Hey guys, it's Chili here. Welcome back to Intermediate C++ Tutorial 24 Part 2. Today we're looking at the unordered associative containers, unordered map, and its ilk. Now the main difference between unordered containers and ordered containers is spoilers. The unordered ones are not in order. If you iterate over the elements, you will not generally get them in the order of the keys. They'll be in just random order. And this is important because by relaxing the condition that they are ordered, that allows us to use a data structure called a
hash table.
And a
hash table
is very fast. Take a look at this page here. A dude did a comparison in performance between ordered maps and unordered maps. And we can see here, as the number of elements in the container increases for a map, it gets more and more expensive to do an insertion. But for an unordered map, it stays relatively the same. It's constant time complexity for insertion, big O of 1. And if we go down here for lookup, we can see here the same picture. As you have larger and larger containers, your map gets worse and worse, but your unordered map stays the same. Unordered map is the college girl of associative containers. I keep getting older and older, and they just stay the same age. So whenever performance is a concern, unordered map is going to be your go-to because it just kicks the shit out of map. So now, hopefully I've got your attention. Let's take a look at what goes into using an unordered map. Obviously, you're going to include unordered map, and you declare it like this, unordered map. Same as map, you give it a key type and a value type. And I'm just initializing it here with an initializer list of pairs. And you can do this with map. There's no difference here between map and unordered map. I'm just doing it a little different this time around. But as you can see here, looking at this code, the interface for map, or unordered map, is pretty much the same as the interface to map. They both adhere to the same core concepts of a map type. So if you want to do a lookup, you can do a lookup with square brackets, but I'm doing it here with map.find. So I give it a key, and it will give me an iterator to the corresponding element. And as long as that iterator does not point to the end of the container, that means that the element or the key existed, and I can do iterator pointer to second to get the associated value out of that. But if the iterator returned is an end iterator, that means that the key did not exist, and then I'll just put out an error message. And you can see here, if I give him a 5, gives me the integer 5 out. But if I give him a 5, that ain't a valid key, bro. So you can see here, it's very similar to working with a map, and that's great news because that means we don't have to learn a whole bunch of new shit. And in this video, I'm going to mostly focus on the differences between unordered map and map. But before we get into the details of unordered map, let's look at how a hash table actually works, because understanding the underlying data structure is actually quite useful to understand how the container works and why it is the way it is. So let me start with a question here. Let's say you've got to store some key value pairs, and the keys are going to range from 0 to 9999. So you've got 10,000 possible keys. And you want to store that. You want to be able to insert and look up very fast. So what kind of data structure would be the fastest for you? Well, the answer is it's going to be an array, right? You just have an array of values, and then the indexes are the keys. So if you want to look up, you just access the array by index, and you've got your value. That's pretty much the fastest you're going to get. Now, what's the problem with this? Well, now let's say our keys don't go from 0 to 9999. Let's say our keys are the full 32-bit integer range. That means that we would have to have an array of about 4 billion elements in order to do our storage to be able to look up any key. And that's a lot, because let's say in general, we only expect to insert maybe 1,000 elements. That means that the vast majority of the space occupied by this container is going to be wasted. Now, what a hash table does is it allows you to get that quick access of an array, but without using a shit ton of memory. So let's say you've got an array here, and it's got, I don't know, it's got maybe like 10 elements in it. And we're going to call these elements buckets. So these are our buckets. And now you want to insert key value pairs into your buckets. So how do you do that? You've only got 10 buckets, let's say, but your key can range from 0 to 4 billion. So what you need to do is you need a function that maps from your key type to your bucket number. And this function is going to be called your hash function. So you take key types, you map them to a bucket number, and then you can store your key value pair. So let's say we're mapping number 69. That is going to map to a bucket number, and let's say that maps to bucket number 1, 2, 3, 4. And then you're going to store 69 and whatever value, sex, into bucket number 4. Then when you want to do a lookup, let's say you want to look up the value or the key 69, again, you run your hash function on 69. It tells you that's bucket 4. And then you look into bucket 4 and you get the corresponding value there. It's that easy. Now, there are some problems with this. The biggest one, the most obvious one, is because you're mapping 4 billion values onto a space of, I don't know, maybe 10, you're obviously going to have different values that map to the same bucket. So 69 maps to bucket 4, but 420 with this hash function also maps to bucket 4. And that's a problem because if I look up 420, it's going to give me the key to 69. So how does this work? Well, let's say we're going to insert 420 into our hash table here. So we hash it. It turns out to be, again, bucket number 4. So we look up here. We see that this bucket is already occupied by 69. So what do? Well, we use a linked list to store our elements in our buckets. So 69, element 69, or node, this node that stores this element, is now going to point to 420. Weed. And there you go. So now this bucket stores 69 and 420. And when we do a lookup, let's say we try to look up 420. We run the hash on it, tells us bucket 4. We look into bucket 4. We look at the first node. It stores 69. That's not what we're looking for. So we go on to the second node. It stores 420. And then we return, the corresponding value. And we call this thing here, we call this a hash collision when you've got multiple elements stored in the same bucket. That's a hash collision. You want to avoid that because this is a linked list, and following linked lists is very slow. Now, there's a couple of ways to avoid that. Way number 1 is have lots of buckets. The more buckets you have, the less chance of you having a hash collision. Number 2 is you want a hashing function that scatters your values randomly and with a uniform distribution. So you don't want a hashing function that tends to clump all your values together in one part of the hash table. And you don't want one that's highly predictable so that patterns of numbers will tend to hash to the same bucket. So hash functions, choice of the hash function is very important. Speaking of hash function, you might be wondering how you can hash something like a string, right? So if I've got a string, how do I hash this into a bucket number? And the answer is, a string is just it's an array of characters, right? And every character is just a number. So what you do is you hash the numbers together cumulatively. You hash this number with the next number, with the next number. I don't know what the ASCII codes are for these, but you hash them all together and you build that up, and the final result hash number is your hash number. And in general, hashing is actually a 2-step process. You've got a general hash function, which is going to take something like a string or an int, and it is going to hash it to a size t, which is going to be, a 32 or a 64-bit int. So hash function will take your key type and hash it to a size t. And then inside the container, this size t is then going to be reduced or distributed to the size of the hash table, the number of buckets. So it's a two-step process. The general hash to the size t, and then the reduction from size t to n buckets. And this reduction step, this is taken care of by the container itself. You don't have to worry about that. You just have to worry about the general hashing. And the standard library provides general hash functions for all the standard types. Now, I know my diagrams are amazing and that's all you really need in life, but let's look at a little visualization of hashing. So if I insert a value, let's insert the value 4, and it is going to put that into bucket number 4. Now, the hash function that this algorithm is using is a very simple one for demonstration purposes. You give it an int, and it just uses that int directly as the bucket number. So the hash function, the general hash function, just is the value itself. There is no operation applied to it. And then the reduction is just mod. So this is going to mod 13, I believe, mod 13. So if I put a 13 in here, it is going to go to bucket 0, because 13 mod 13 is 0. And so now if I put a 0 in here, we've got a hash collision, and it just inserts that as a linked list. And then the end node here is just pointer to null. That's the terminus of the linked list. And there you go. There is your hashing all done. Just buckets of linked lists. That's the basic way. Now, there's actually basically an infinite number of ways you can implement a hash table. There's tons of different implementations. But luckily, we don't have to really worry about implementation details when we're working with the unordered map. We don't care how it implements its hash table, just as long as we know it's a hash table. Now, there are a couple of requirements for the key type of a hash table. First of all, obviously, you're going to have to provide a hash function for your key type. Second of all, you need to also provide a comparison, just like with the normal map. You might be wondering why you need the comparison. Well, when you do a lookup, say we're going to look up 13, it hashes 13 to find the bucket, but then it has to do a comparison to find the actual element in the linked list. So find hashes, and then it does comparisons until it finds the one it's looking for. Or if it doesn't find it, then it returns iterator to end or whatever. It doesn't matter. So you need a hash function and you need a comparison function for your keys. That's the two major requirements. So to make things interesting, let's try to map from vec2 to a string. So I'm going to create my unordered map. I'm going to insert some pairs into it, and then I'm going to try to look up one of my inserted pairs. Now, if we try to build this, you might expect we're going to get a bunch of errors. And to save you from I'm not going to go and read through all these because template errors are cancer. But basically, we don't have a hash and we don't have a comparison, and that's a problem. So let's give this dude hash and a comparison. So the comparison functor is going to be the same as we had in the last video, basically. I made it a template so that it works with any kind of vec2, v2, or a double vec2, or whatever you want. Actually, this should be an integer vec2 though, so let's change that to v2. But yeah, so here's our comparison function, and now we need a hashing function. Now, hashing is a bit of an art, really. To construct your own hashing function from scratch requires a lot of knowledge of cryptography, stuff like abstract algebra and discrete math, things like, fields, groups. You need to be familiar with operations like modulus, shifting, exclusive OR. There's a whole bunch of bullshit. But luckily, you don't have to know any of that to hash your shit, because all of your classes, all of your data structures are built out of basic types. And basic types already have hash functions defined in the standard library. So all you need to be able to do is combine hashes from your basic types to create a hash over your entire object, or over the part of your object that you want to include in the hash key. So how do we combine hashes? Well, there's nothing in the standard library for that, which is kind of stupid. But, well, a simple Google search will turn up this Stack Overflow question: how do I combine hash values in C++? And the answer is do it like they do in Boost, which is you use the standard library hasher to hash one value, and you combine it with another hashed value. And so you hash the value that you're trying to combine into the combination, and then you add some magic number bullshits, and you do a little bit of shifting, you add all that shit together, you exclusive OR, and there you go, there's your combined value. So let's apply this to the simple situation of hashing together two ints. So again, we create a struct. It's got a single templated operator here. We're going to template it a little differently. We're going to template on vec2, the template type of t. So that means that t now represents the actual element type, whether it's int or whether it is float or whatever. Now we want to hash that. So we need a Steed Hasher. So Steed hash, and it's got to be a type t. And we'll call this one the hasher. And now we want to get our two hash values. So we'll go auto hash 1. Let's call this one hash x is equal to hasher of vec.x. And then we're going to go auto hash y is equal to hasher of vec.y. So vec.x is going to be our seed, or hash x is going to be our seed, and vec.y is going to be the other one. So how do we combine them? Well, let's take a look at this again. So this is the expression. We're just going to paste that into here. Now the seed is hash x. So let's put that there, and there, and there. And hash y is this one right here. And there you go. And we don't need to, we can just do it like this. Yeah, we'll just do it like this, and then we'll return hash x. And there you go. We've just hash combined the x and y of our vector. And this works for float, int, car, any kind of vec2 that you want, really. And it should now just work. We have our comparator, we have our hasher. We need to tell our unordered map about them. We can see here, unordered map template takes the key type, the value, and then it takes the hash and the equal to. Oh, it doesn't use a less than comparator. It actually uses an equal to comparator. That's right, because it's checking to see if keys are equal to each other. So you don't pass it a less than, you pass it an equal to. So that's easier. Does vec2 to have an equal? I don't believe yeah, it does have an equal. It has an operator equals. So actually for vec2, the story is a lot easier than you would think, because you don't have to pass it a custom comparator. The default one will work because vec2 defines its equals operator. So that makes life easier. So all we need to do is pass the hash, which is going to be the hash type, which is going to be hash vec2. And there you go. If I run this, I think it'll build. I believe it'll build. I hope it'll build. It does build. And if we run it, 99, which is the thing that corresponds to this vec2. So there you go. There's your hash. And it's actually easier than I thought it was going to be, because we had already implemented the equals. And it's common that your types are going to implement equals. So yeah, not bad. Now, unordered map is by default wired to use Steed hash. And you can actually inject template specializations for Steed hash into the Steed namespace for your own custom types only. So what would that look like? Well, here's what the template specialization looks like. You have to put your thing in namespace Steed. And this is actually the only real time where you're allowed to inject things into the namespace. And you're going to specialize the template hash for the type va2. And the rest is basically the same. Just your operator takes a va2, you're going to hash ints, and you do your shit. And if you do that, what you can do actually is now you can just say unordered map va2 and Steed string, and it will use your specialization of Steed hash here. If I build this, shouldn't be any errors. There you go, no errors. So a little bit of sexiness here, injecting your own template specializations into the Steed namespace. So you can look that up if you're interested. But it's just a little bit of sugar. It's fine just to create your own standalone structure and pass it in here in the template parameters of the unordered map. All right, finally, let's take a look at the interface for unordered map, and let me just give you an overview of what the things do. So basically, constructor, destructor, iterators, empty, size, clear, insert, in place, all these are going to be the same idea as what I've told you about map, so we don't need to worry about them. Lookup, again, same idea. You'll notice here, you don't have a upper bound or lower bound. Those only exist for the ordered types. Now, the thing that's different here is the bucket interface and hash policy. So bucket interface allows you to actually fiddle with the buckets of the hash table. You don't usually do it, but if you want to, you can. So this begin and end, this is the normal one you're used to. It'll iterate over all the elements in the container. This iterator here is different. It takes a parameter, basically an int, and that is the index of the bucket, and it allows you to iterate over all of the elements in a specific bucket. So you can choose a bucket and iterate over all the elements only in that bucket. Here you can get the number of buckets, you can get the maximum number of buckets, you can get the number of elements in a specific bucket. Basically, you can see how many collisions you have in a bucket, and returns a bucket for a specific key, size type bucket. This one allows you to give it a key, and it will tell you the index of the bucket that corresponds to that key with the current hashing function. So this will allow you to fiddle with buckets, not particularly useful for your general applications, but I don't know, might be useful sometime. Now, hash policy is more when you start wanting to tune your hash table. So load factor basically tells you average number of elements per bucket. So when your table starts to become overloaded, you've got a bigger chance of having a lot of collisions in your hash table. And what the hash table does, what the unordered map does, is when the load factor gets too high after inserting a lot of elements, it will automatically rehash the table. So it'll increase the number of buckets, and then because the number of buckets are different, it has to now rehash all of the elements and put them into the new container. So it's the same idea as a vector growing. And the max load factor tells you the point at which the container will be rehashed. It'll be grown and rehashed. So you can you can set this yourself. So you can tune this to have it rehash at higher factors or lower factors. And you can also manually rehash and give it a number of buckets to rehash to. And you can reserve space, which is like rehashing, but instead of giving it a number of buckets, you give it a number of elements, and then it will decide based on that number of elements what number of buckets it should be using. And there you go. So this allows you to basically tune the growth behavior of your container. So the two main ways that you tune the performance of a hash container is A, with the hash function itself, and B, with the hash policy. But it's not something that you do that often. Generally, just stick with the standard hash functions, combine them together if necessary, and stick with the standard hash policy, and you should be fine. You'll still get great performance. And just like for map, unordered map also has unordered set, unordered multi-set, and unordered multi-map, and the relationship between them is generally just the same as the relationship between these guys. So I don't need to go over that again. Once you understand how unordered map works, you can figure out how the set and the multi containers work as well. It's not that big of a deal. Now, one question you might be having is, if the unordered containers are so much faster and better, why do we even have normal map at all? So, well, let's take a look at that. I mean, the first advantage for why you might want to use map instead of unordered map is maybe you don't want to write a motherfucking hash function. Maybe you feel lazy. If the performance doesn't matter, save yourself some time, use a normal map. Who cares if the performance doesn't matter? The other main reason is if you want to iterate in order, then you might want to use a map because it's more convenient. In general, if performance matters and you want to iterate in order, I would say maintain maybe 2 containers, one that has a hash table, and then another one is just a vector or something. And then you can iterate in order, and you can look up random access. But maybe, I mean, that's more work, right? If you don't care about performance, just use a map. You can iterate in order and you can look up, and it's still, pretty fast. One third advantage that a map has over an unordered map is you can find keys that are close to a certain key. So by using lower bound and upper bound, I can, for example, use lower bound, returns and iterates the first element not less than the given key. So by doing lower bound of 69, even if there is no 69 in my container, but there's a 70, it will return me the 70. So you can kind of give it values, and it will give you the closest one that's higher and the closest one that's lower. And that can be useful in certain situations. All right, let's have a little bit of light homework for a change. Pretty simple. Create a hash function for the struct pub that uses all of its members. That's it. You got a string, a v2, an int, and a char. Hash them together, and that is your assignment. And of course, you're going to want to test that out. So you're going to want to create an unordered map of pubs. We'll map them to string. Doesn't matter really what you map it to. And you're going to insert some in here. I'm using the constructor to insert just some pairs in here. And then you're going to want to do a lookup. It is that simple. Now there is one condition, and that is that you're not allowed to modify this struct. You're not allowed to add members to it or remove members. So yeah, you're going to want to get the pub to work with the unordered map. So good luck with that, and I will be posting a solution video in the near future. But there you go. There is the unordered map in a nutshell. Fast lookup for you, mate. And that's the end of this video. Next time, stay tuned. I think the next video is going to be the last one in the entire series. We're going to talk about basically a little bit about functional programming in C++ with std function. And it's going to be a good time. So until then, thanks for watching. Hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more C++.